Before the first star ever ignited, before galaxies existed, before there was anything bright enough for a telescope to see, the universe was already carrying a signal. Not light. Not sound. Something far stranger. A primordial hum written into the fabric of spacetime itself. In 2026, a new stream of deep space observations is giving scientists an unprecedented way to search for that ancient signal: gravitational waves, tiny distortions in spacetime that can travel across the universe without needing light, stars, or galaxies to carry them. And if we can isolate a genuine primordial background, we could be looking at something no ordinary telescope has ever been able to see. The universe before the universe became transparent. To understand why this matters, we have to travel back almost to the beginning. The early universe was an extreme environment. Matter was compressed into an incredibly hot, dense plasma, and photons were constantly scattering off charged particles. Light existed, but it couldn't travel freely across space. That creates a fundamental limit for traditional astronomy. The oldest electromagnetic light we can directly observe comes from the cosmic microwave background, released roughly 380,000 years after the Big Bang, when the universe finally cooled enough for electrons and nuclei to combine into neutral atoms. Before that moment, the universe was effectively opaque to light. So when astronomers point powerful telescopes toward the deepest reaches of space, they aren't seeing the actual beginning. They're seeing the universe after it had already undergone a massive transformation. But gravitational waves are different. They aren't electromagnetic radiation. They're ripples in spacetime itself. Imagine dropping a stone into a perfectly calm pond. The stone doesn't travel outward as a visible object. Instead, it creates waves that spread across the surface. Gravitational waves work on a vastly more fundamental level. Violent changes in the distribution of mass and energy can create distortions that propagate through spacetime. And unlike light from the early universe, those waves can potentially carry information from epochs that electromagnetic telescopes simply cannot access. That is why scientists are searching for a primordial gravitational wave background. The idea is extraordinary. Instead of looking for ancient light, we search for ancient spacetime vibrations. A kind of cosmic acoustic imprint. The 2026 data stream becomes especially interesting because researchers are pushing observations toward signals that could have originated from extremely early processes in the universe. But there is an enormous challenge. The primordial signal we're searching for is expected to be extraordinarily weak. Modern space-based detectors have to distinguish possible cosmological gravitational waves from a universe filled with other sources, merging black holes, neutron stars, compact binaries, instrumental noise, and countless other disturbances. It's like standing beside a roaring ocean and trying to determine whether one particular ripple was created billions of years ago by a wave on the other side of the planet. That is the real quest. Not simply detecting gravitational waves, but determining whether some portion of the signal is truly primordial. If such a background is confirmed, it could become one of the most powerful probes of the early universe ever developed. Because gravitational waves could preserve information about conditions that disappeared long before the cosmic microwave background was released. They could potentially tell us about processes associated with inflation, phase transitions, primordial particle physics, or other extreme events that occurred when the universe was unimaginably young. And that changes the question. Instead of asking, what did the early universe look like? We could begin asking, what did the universe physically do? The distinction is enormous. Light gives us an image. Gravitational waves can give us a record of motion and dynamics. They could allow us to study an era where there were no galaxies, no stars, and no planets. Yet the fundamental structure of the cosmos was already being established. This is why scientists sometimes describe gravitational waves as a new sense for astronomy. Our eyes detect visible light. Infrared telescopes reveal heat. Radio telescopes reveal long-wavelength electromagnetic signals. But gravitational-wave observatories give us an entirely different way of experiencing the cosmos. They allow us to detect the movement of spacetime itself. And the deeper we push this technology, the farther back in cosmic history we may be able to travel. There is an important distinction, though. The current data should not be described as a confirmed recording of the exact instant of the Big Bang. That would go beyond what the evidence can establish. The primordial gravitational wave background remains a difficult target, and separating an authentic cosmological signal from astrophysical foregrounds and detector noise is one of the great challenges of modern gravitational wave astronomy. But that uncertainty is exactly what makes the search so important. Because somewhere inside that enormous stream of data could be information from a universe that existed before the first stars. Before the first galaxies. Before the first atoms. Before the oldest light we can see today. And if scientists eventually isolate that primordial hum, they won't simply have discovered another astronomical object. They will have opened a new observational window into the earliest physical history of reality itself. For the first time, we wouldn't just be looking back toward the beginning. We would be listening for its imprint. A signal that crossed the expanding universe for billions of years, carrying information from an epoch that no ordinary telescope can ever see. The universe may have gone silent in many ways. But spacetime never completely forgot. And hidden inside its faintest ripples may be the oldest message humanity has ever received. But detecting the primordial hum would only be the beginning. The real question is much bigger. What would that ancient signal actually tell us? Because buried inside a gravitational wave background could be information about physical processes that happened so early that they left almost no other observable trace. To understand the possibilities, we have to go even deeper into cosmic history. The universe was not simply born and then immediately filled with stars and galaxies. There was a sequence of extraordinary transformations. Space expanded. Temperatures fell. Particles interacted. Fields changed their states. And eventually, the matter that would become everything we see today began taking shape. One of the most important ideas scientists are investigating is cosmic inflation. According to the inflationary picture, the universe underwent an incredibly rapid expansion during an extremely early phase of its history. In an unimaginably short period of time, microscopic quantum fluctuations could have been stretched to enormous cosmic scales. Those tiny fluctuations may eventually have become the seeds from which galaxies and the large-scale structure of the universe formed. But inflation also raises another possibility. If spacetime itself was fluctuating during this period, those fluctuations could have generated gravitational waves. And if those waves survived the expansion of the universe, their imprint could still be surrounding us today. Think about what that means. A detector on or around Earth could potentially measure a signal generated before stars, planets, and galaxies existed. The waves would have crossed billions of light-years of expanding space.